Hi Year 11, this is the Paper 2 Foundation Physics revision video. Good luck with the exam when it comes. Right, first topic, forces. First idea is our idea about scalars and vectors. Things which are scalars in science are things which only have a size. Things that are vectors in science are things that have a size and a direction. So when we measure things in science and they only have a size, they're a scalar. For example, speed is a scalar. Remember, the S's go together. Scalar, size, speed. Things that are V's go together. Velocity is a vector. So vectors have a size and a direction. Scalars only have a size. So forces, for example, are all vectors because they have a size, how big the force is, and they have a direction, the direction that the force pushes or pulls. So when you're drawing a vector, you can always draw a vector as an arrow, with the direction of the arrow showing the direction of the vector and the size of the arrow showing the size of the vector. So remember, scalars only have a size, vectors have size and direction. So one of the forces we're going to deal with is weight. Now remember, the weight of something is how heavy it feels, and that's caused by gravity. Now that means that your weight can be different in different places. For example, I feel heavier on the Earth and I feel lighter on the Moon. That's because gravity is stronger on the Earth and weaker on the Moon. But my mass never changes. The example here shows that the person's mass is always 56 kilograms, no matter whether they're on Earth or on the Moon. So mass always stays the same, but weight changes because of the force of gravity. Now, when we draw a force arrow to show the force of gravity, we must draw it coming from the center of gravity. So we don't draw it coming from anywhere other than the center of gravity on an object. So when you're given a diagram, draw your force arrow coming from the center of mass. Because weight is a force, it is measured using a Newton meter and it's measured in newtons. So weight in newtons can change, but mass in kilograms always stays the same. The required practical that goes with the weight and force idea is the stretching a spring and the extension of a spring practical. To carry out this practical, you need to set up a stand with 2 clamps on it. Remember, I need 1 clamp for my spring and I need 1 clamp for my meter ruler. Once those are in place, then I can measure the length of the spring to begin with. And once I know the length of the spring to begin with, then I hang a 100 gram mass on my spring. Then I measure the new length of the spring and work out the extension. The stretched length, take away the original length. I keep repeating that until I've added 500 grams. So when we're setting up this required practical, remember we need to set up 2 clamps, 1 for the spring and 1 for the ruler. Now when I plot the results of this experiment with the extension of the spring and the force I use to stretch the spring, I get a graph that looks like this. To begin with, as I increase the extension, I need to increase the force, and the line is perfectly straight. This is because the extension of a spring and the force I need to stretch it are proportional. We say that the first section of the graph, extension and force, are directly proportional. But eventually we stretch the spring so much that the spring is stretched out of shape and the line is no longer straight. So because the graph isn't directly proportional anymore, we call that point on the graph the limit of proportionality. You might need to mark that on a graph, and the limit of proportionality is where the line on your graph starts to curve. So that's the forces topic. Next topic is motion. A lot of the content on the motion topic will be about distance time graphs and velocity time graphs. Now, a distance time graph tells us how far an object has traveled as time ticks along the x-axis. Distance time graphs tell you about speed. So the steeper the line on your graph, the greater the speed. So in this example here, I've got a distance time graph that shows me an object was moving at a steady, slow speed to begin with, because I have a not very steep line. Then I have a horizontal line, no gradient, so I can tell the object was stationary. Then the object moved at a fast, steady speed, because the line is steeper. So distance time graphs tell you all about speed. The steeper the gradient, the faster the object is moving. If the line is horizontal, it means the object has stopped. The other type of graph is a velocity time graph. Now, velocity time graphs tell us about acceleration, whether an object is speeding up or slowing down. So now the gradient tells me if an object is accelerating, if I've got a positive uphill gradient, or going at a steady speed, if I have a horizontal or zero gradient. A negative or downwards gradient tells me that an object is decelerating or getting slower. So remember, velocity time graphs are about acceleration. The steeper the line, the greater the acceleration. On a velocity time graph, a horizontal line means a steady speed. Now, one special velocity time graph we might think about is the velocity time graph when a car or another vehicle stops. If we look at our velocity time graph, we can see it's going at a steady speed, and then it slows down until it stops. Now that's telling a story about the distance something needs to travel. And that journey is broken into two parts. We say that the stopping distance is equal to the thinking distance added on to the braking distance. So the thinking distance is the distance that the car travels during someone's reaction time. The braking distance is how far the car travels when the brakes are slowing the car. So stopping distance equals thinking distance plus braking distance. Now some things can increase thinking distance. For example, using alcohol, drugs, being tired, or being distracted by things like a mobile phone. That will make your reaction time increase, and so your thinking distance would increase. Remember, if you're going faster, your thinking distance will also increase. Your braking distance is affected by things which can change the amount of friction. So for example, an icy road, a wet road, poor brakes, or poor tires will mean there is less friction, and so the braking distance will increase. Make sure you know the difference between factors which increase the thinking distance and increase the braking distance. All of these will make the stopping distance get bigger. So remember, your stopping distance is the grand total of your thinking distance plus your braking distance. When we write down the rules about how things move, there are three laws written down by Isaac Newton. The first law written down by Isaac Newton says that an object will stay the same unless there is a force acting on it, an unbalanced force. For example, an object sat still will stay sat still unless there is an unbalanced force on it. But if an object is moving, it will keep moving at a steady speed in the same direction unless a force makes it speed up or slow down. So Newton's first law explains that forces make things speed up or slow down. If there is zero force on an object, then it will stay the same speed and moving the same direction. Newton's second law tells us the amount of force we need to make something accelerate is equal to the mass times the acceleration we want. In other words, if we increase the force, we get more acceleration. But if we increase the mass of something, we get less acceleration when we push or pull it. Finally, Newton's third law tells us that objects, when they're pushed or pulled, make a pair of forces. Forces come in pairs. The important thing about the pairs is that the pairs are the same size but opposite directions. So Newton's third law says we get pairs of forces, opposite directions and equal size. Newton's first law says a zero resultant force means there's no change in speed. Newton's second law says the acceleration of an object is proportional to the force you push or pull it with. And Newton's third law says that forces make pairs of equal size and in opposite directions. Now, one special example of a velocity time graph and the forces making something accelerate is the forces on an object making it get to its top speed or terminal velocity. One of the main examples we use is a skydiver falling until they get to a steady speed. The velocity time graph tells me that they accelerate, they keep accelerating, and then they get to a steady speed. Accelerate, keep accelerating, steady speed. We need to explain why they get to a steady speed and don't just keep accelerating forever. To start off with, there is just a gravity force pulling the skydiver down. So they accelerate, their velocity increases. But the faster they move, the more air resistance force they feel. To begin with, there is no air resistance. As they move faster, they feel a small air resistance force. And eventually they feel a very large air resistance force. So they accelerate, they keep accelerating, but eventually the gravity force and the air resistance force are balanced, so they move at a steady speed. The faster they go, the bigger the air resistance force. So they get to terminal velocity, their top speed, when air resistance equals the size of the gravity force. As their speed increases, their air resistance force increases. Right, third topic is waves. Now, when you get a diagram of a wave, you're going to need to be able to label the wavelength and amplitude of a wave. Remember, the wavelength of a wave is the distance from one peak to the next peak on a wave. So you must, if you're labeling it, draw a line which goes straight from one peak of a wave to the next peak of a wave. The amplitude of a wave tells us how high it is from the middle up to the peak, or from the middle down to one trough. Remember, we measure the amplitude from the middle of the wave, from the flat starting position where there is no wave. So wavelength, the distance from one peak to the next peak. Amplitude, the height of a wave from the middle up to the peak. Now, the important fact about all waves is that all waves are made by a vibration. Something needs to move backwards and forwards or up and down to make a wave. When a wave is made, a wave transfers energy. It takes energy from one place to another. So all waves are made by vibrations, and all waves transfer energy. Now, that's important when we look at the two different types of wave. The two different sorts of waves are transverse and longitudinal wave. And to understand the difference between them, we need to remember that all waves are made by vibrations and all waves transfer energy. All waves are made by vibrations and all waves transfer energy. So, for example, in a water wave, the vibration that makes the wave is an up and down motion as the drop of water makes the water splash up and down. But the energy is carried across the water. So what we say is that the vibrations are perpendicular at right angles to the direction the energy is transferred. Now, to help you remember that, we remember that T, transverse wave, starts with the letter T, and the letter T has a big right angle in it. So the vibrations that make the wave are perpendicular or at right angles to the direction the energy is transferred by the wave. In a longitudinal wave, we see the vibrations that make the wave are parallel to the direction the energy is transferred. So we say that a longitudinal wave is one where the energy transfer is parallel to the direction of the vibrations. Now, we remember that looking at the two L's in longitudinal, which help us remember the two parallel lines which make longitudinal. Water waves are a good example of transverse waves. and longitudinal waves, a good example of those is a sound wave. So again, could be a little foremarker. When we make a transverse wave, the vibrations are perpendicular to the direction of the energy transfer. When we make a longitudinal wave, the vibrations are parallel to the direction of the energy transfer. Now, one special sort of transverse waves are the electromagnetic waves. Electromagnetic waves are transverse waves. The vibrations that make them are perpendicular to the direction the energy is transferred. But the special thing about electromagnetic waves is they travel at the speed of light. All the waves in the electromagnetic spectrum travel at the speed of light. And the other special thing about them is they can travel through a vacuum. In other words, they can travel through space where there is no particles. So the waves of the electromagnetic spectrum are radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. And we have to learn them in this order because we're learning them in order from the longest wavelength, which is radio waves, up to the shortest wavelength, which is gamma rays. We're learning them in lowest frequency, radio waves, up to the highest frequency, which is gamma rays. And we're learning them from lowest energy, radio waves, to the highest energy, gamma rays. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. Now, all these waves are used in different ways by humans, and some of them are dangerous to humans. So it's important you can match up the name of the wave with what it's used for. So for example, radio waves are used to send your radio and Freeview TV signals. Microwaves are used to send your mobile phone and satellite TV signals. Infrared waves transfer heat energy, and they're used in remote controls, and they're used in heat or thermal cameras. Visible light, the light we can see, is used by things like cameras and fiber optic cables, which carry light signals through thin glass wires. Ultraviolet rays are used in sunbeds and also in efficient lamps. X-rays are used to detect broken bones for people in hospital. And gamma rays can be used to treat cancer by killing cancer cells inside people. Now, the danger of electromagnetic waves increases as we go from longer to shorter wavelength, as we go from lower to higher energy. For example, radio waves and microwaves aren't dangerous to people. Infrared waves could burn you if you're exposed to enough of them, and visible light is only dangerous to your eyes. Now, ultraviolet, X-rays, and gamma rays are ionizing. They can ionize your DNA and could cause cancer. Because ultraviolet cannot penetrate deep through the cells of your body, it can only damage the skin cells, and so ultraviolet electromagnetic radiation can cause skin cancer. X-rays and gamma rays can cause cancer in your body. So remember, when you're learning these in order from the longest to the shortest wavelength and from the lowest to the highest frequency. You may be asked to describe the required practical to investigate which colors are the best emitters or absorbers of infrared radiation. Now, infrared radiation are the electromagnetic waves that carry heat energy. So to detect how much infrared radiation is coming off an object, we can measure its temperature. In some of these experiments, we can use just a thermometer to check the temperature. Or in some of the experiments, you may be given an example of using an infrared detector. To investigate the different colors, to see which is the best emitter of infrared radiation, the ones which give out infrared radiation the quickest, you could fill 3 different color containers with water which is the same temperature. If you start a stopwatch and then measure their temperature after 5 minutes, the one which is the best emitter will have decreased in temperature the most because it has emitted the most infrared radiation. If you want to see which is the best emitter of infrared radiation using the Leslie cube, which is a metal cube painted 4 different colors, we can fill the Leslie cube with water. So the same temperature water is touching all 4 sides of the cube. And we can measure the amount of infrared each side emits using an infrared detector. Now, when we carry out these experiments, we always find that matte or dull black colors are the best emitters of infrared radiation. For example, its temperature will decrease the most when we test it in this experiment, or it will give the highest reading of infrared being emitted in the Leslie cube experiment. Shiny white surfaces are the worst emitters of infrared radiation. They will cool down more slowly, or they will give a lower infrared reading in the Leslie cube experiment. You could always check to see if they absorb or soak up the infrared radiation, and you should also find that matte black, dull black colors are the best absorbers of infrared radiation, and shiny white colors are the worst absorbers of infrared radiation. So in all those experiments, we should be seeing that matte black colors are the best emitters and absorbers of infrared radiation, and shiny white colors are the worst emitters and absorbers of infrared radiation. The other experiment you might be asked to do on the waves topic is one where we try to investigate the speed of a wave using the ripple tank, a small water-filled pool which we shine a light through so we can see the ripples in the water. Now, to find the speed of a wave, we're going to use the equation which says the speed equals the frequency of a wave multiplied by its wavelength. You're going to need to explain how you can use this equipment to measure the frequency of the wave and the wavelength of the wave. To measure the wavelength of the wave, we put a meter ruler beside the piece of white cardboard where we can see the waves. We measure the length of 10 waves using the meter ruler, and then we divide by 10 to get the length of 1 wave. You're allowed to take a photograph of the white card if you wish, because it's hard to measure the length of the waves when they're moving. To measure the frequency of the waves, we count the number of waves that go past the end of the ruler in 10 seconds. Then we divide that by 10 to get the frequency. To work out the speed of the wave, we multiply the wavelength by the frequency. So the ripple tank experiment is going to ask you how you measure the wavelength and frequency of the wave. Remember, wavelength we get by measuring the length of 10 waves with a ruler and dividing by 10. To get the frequency, we count the number of waves which go past in 10 seconds with a stopwatch and divide by 10. Final topic is magnetism. Now, for your magnetism questions, you're very likely to have to draw the magnetic field around a bar magnet. Loops on the side of the magnet and curved lines from the poles. Remember to add one straight line at each pole. Now the arrows show the direction of the field, and the arrows always go away from the North Pole to the South Pole. So one arrow on each line going away from the North Pole and to the South Pole. Look at the arrows on both sides of the magnet. You'll see they point the same direction, from the north to the south. Now the magnetic force of a magnet can attract some metals, not all metals. You have to remember that the 4 magnetic metals are iron, steel, cobalt, and nickel. So a North Pole and a South Pole will always attract magnetic metals. Only 2 magnets with the same pole can repel or push each other apart. Magnets with opposite poles will attract. Now when we look at the field around a magnet, we can tell where the magnet is strongest by looking at how close the lines are together. The more close the lines are and the more lines there are in a space, the stronger the field is. So that way we can see that the poles of a magnet are where the field is strongest, and the sides of a magnet are where the field is weakest. More lines meaning stronger, fewer lines meaning a weaker magnetic field. Now a magnet which always has a magnetic field is called a permanent magnet. but some objects can become magnetic when we put them into that field. For example, when we put paper clips on the end of a magnet, they become magnetic and they are able to attract other paper clips. Now that sort of magnet, which only becomes magnetic when you put it in a field, is called an induced magnet. So my bar magnet is a permanent magnet which always has its magnetic field, and the paper clips are an induced magnet which has only become magnetic when we put it into the magnet's field. Now it's worth noticing that the induced magnet is always attracted to the magnet that made it magnetic. For example, this end of this paper clip would be a north pole and this end would now be a south pole. That means on this magnet there is now a north pole and a south pole. Remember, the induced magnet is always attracted to the magnet that made it. Permanent magnets have their own magnetic fields, and induced magnets only become magnetic in a magnetic field. Now another way of making induced magnets is by using electric current. When we put electric current down a wire, then that wire gets a magnetic field around it. But the shape of the magnetic field is a circle, with the circles getting further apart to show that the field is getting weaker as you get further away from the wire. Now to remember the direction that the arrows go around the wire, we use the right hand rule. We imagine that we've got our fingers around the wire of our right hand with our thumb pointing in the direction of the current. Now our fingers then tell us the direction of the magnetic field around the wire. So if the current is going up the wire like this, then I imagine holding it with my right hand, and I can see that the circles go around the wire anti-clockwise. I can see if the current is going down the wire like this, I'd imagine holding it with my right hand, but now the fingers would curl clockwise around the wire. So the right hand rule is used to tell us what the field around a wire is. The fingers stand for the direction of the field, and the thumb points in the direction of the current. Now, if we make a piece of wire into a magnet without its magnetic field is very weak. So to make a better magnetic field, we turn the wire into a coil shape. Now, if we twist a wire into a coil and put an electric current down it, we've made a shape called a solenoid. A coil of wire is called a solenoid. And making the wire into this coiled solenoid shape makes the magnetic field much stronger. In fact, the field around a solenoid looks just like the field around a permanent bar magnet, with the loops around the side and the curved field lines coming out of the North Pole and South Pole, and a straight line through the center of the coil. We say that that's a nice strong field, and we use the word uniform to tell us that it's all pointing in the same direction from north to south. If we add an iron core to that solenoid, we've made an electromagnet with an even stronger field. Now, the advantage of an electromagnet is that it's a magnet which we can switch on and off and make stronger or weaker. For example, if we're picking up scrap in a scrapyard, we can turn the magnet on to pick up the metal and turn it off to drop it. If we want to pick up something heavier, we can make the magnet stronger by increasing the current or weaker by decreasing the current. So electromagnets can be turned on and off, and they can be made stronger and weaker. The final experiment you might have to describe is how you can show the magnetic field around a magnet. An easy method to do that is to cover the magnet with a sheet of paper and sprinkle iron filings on top of the piece of paper. The iron filings will show the shape of the magnetic field. If you need to show the direction of the magnetic field, then we're going to need a small compass which points north and south. We put the compass beside the magnet and we draw a dot to show the direction that it has pointed, and then join the dots at the end. Right, that's all 4 topics. Really good luck in your paper 2. You're going to smash it. Don't forget your calculators. Good luck.